Deep inside the crystalline lattice of a modern battery, a single lithium ion violently forces its way into a graphite matrix. With every microscopic insertion, the atomic structure expands, stresses, and fractures. We have been conditioned to accept a profound illusion. We believe that to store energy, we must inevitably destroy the vessel holding it. Observe this configuration. A standard photovoltaic panel, a copper cable feeding a discarded steel propane tank. That cylinder interfaces with a pneumatic rotary actuator, which is currently illuminating this room. The utility meter remains completely paralyzed. This steel cavity was acquired for $50 at a residential liquidation. It harbors no chemical solvents. It will not suffer structural fatigue. A decade from this precise second, it will encapsulate the exact same kinetic potential it holds today. Half a century from now, the mathematics remain identically flawless. In that exact same 10-year window, the premium lithium-ion cells mounted to the wall of a modern residence will have irreversibly hemorrhaged 20 to 30% of their total capacity. They will conclude their operational existence as a localized ecological toxin, a chemical debt that the global supply chain has no scalable intention of settling. A modern lithium architecture bleeds 2 to 3% of its storage ceiling every single orbital cycle. That decay is not an engineering oversight. It is a calculated design parameter. The electrodes physically erode. The liquid electrolyte chemically destabilizes. The capacity curve only falls. When utility is ultimately breached, the entombed cobalt, lithium, and manganese present a metallurgical nightmare. This $50 cylinder bypasses that nightmare entirely. Its storage medium is the atmosphere itself. Its engineered degradation rate is absolute zero. Its recycling obligation is non-existent because it has no death. To comprehend the engineered silence surrounding this mechanism, we must evaluate the industrial timeline, rewinding to the 1870s. During this era, compressed atmospheric pressure was the undisputed sovereign of energy distribution. From 1881 until 1994, Paris maintained a vast, subterranean pneumatic network. For over a century of continuous, unbroken mechanical respiration, pressurized air surged beneath the cobblestones. It actuated heavy manufacturing looms. It drove commercial printing presses. It synchronized the city's public chronometers. London, Birmingham, and the iron-rich Midlands replicated this architecture. Compressed air was the 19th century's electrical grid, a centralized cardiovascular system powering an entire urban economy. Decades later, in 1978, structural engineers in Huntorf, Germany, finalized the first modern utility-scale compressed air energy storage facility. They utilized subterranean salt caverns to capture surplus electrical generation, sealing immense pressure into the earth to be released upon demand. That specific German infrastructure remains fully operational this morning. It has sustained nearly 50 years of brutal thermodynamic cycling with zero fundamental alterations to its foundational mechanism. The physics are absolute. They have never faltered. Elite energy conglomerates acknowledge this reality, quietly operating massive pneumatic storage facilities across Alabama, California, and the European continent for grid-scale stabilization. The domestic eradication of compressed air was not the triumph of superior engineering. It was the triumph of a parasitic business model. When consumer lithium-ion architectures flooded the market in the early 1990s, they introduced a variable that steel tanks could never offer: predictable mortality. An energy reservoir that shrinks over time is a product that guarantees its own replacement. A steel cavity that holds pressure indefinitely is a product that terminates the transaction. One of these paradigms extracts continuous downstream capital. The other severs the corporate tether forever. The physics of compressed air energy storage operates through three uncompromising principles that elevate it above every chemical battery on the market. The first is potential energy captured through raw pressure. Dictated by the ideal gas law, the energy harbored within a compressed gas is directly proportional to its internal pressure multiplied by its volume. When a mechanical compressor packs ambient air into a rigid steel boundary, it actively translates electrical current into the kinetic tension of a trapped fluid. When that invisible pressure is released through a pneumatic turbine, the stored potential reverts flawlessly back into mechanical torque and electrical generation. Between those two temporal events, the medium remains pristine. The atmosphere does not rust. The steel does not tire. A 20-pound cylindrical vessel, rated to 250 pounds per square inch and charged to 150, will cradle between 3/10 and half a kilowatt-hour of usable reserve. That metric is sufficient to sustain light-emitting diodes through a nocturnal cycle, revive digital communication architecture, or power a compact refrigeration unit. A 100-gallon vessel scales this to meaningful off-grid resilience. It is a bunker of potential. The second principle dictates thermal efficiency, a parameter rigorously quantified by researchers at the Massachusetts Institute of Technology in 2023. When you compress a gas, you physically concentrate its kinetic energy. It generates profound heat. This is the exact thermodynamic mechanism that causes a manual bicycle pump to grow warm. In standard adiabatic compression, that thermal energy bleeds uselessly into the surrounding environment, actively crippling the round-trip efficiency of the system. MIT researchers proved a physical countermeasure. If the mechanical compression is deliberately throttled, allowing the heat to passively dissipate in real time, it achieves isothermal compression. Pair this with an expansion phase that actively absorbs ambient warmth, and the system's efficiency approaches theoretical thermodynamic limits. Their objective was absolute: to render small-scale pneumatic storage mathematically competitive with residential lithium. The third principle exposes a geographic weakness in modern electrochemical grids. Lithium-ion chemistry despises the cold. As ambient temperatures plummet, the internal chemical kinetics of a battery grind to a paralyzing halt. It bleeds total capacity precisely when human thermal reliance is highest. Pressurized air achieves the exact opposite reality. Cold air is inherently dense air. A rigid steel cylinder charged on a sub-zero winter midnight physically contains more extractable kinetic energy than that identical cylinder charged beneath a blistering summer sun. It thrives in the frost. Contrast this elegant permanence with the $50 billion apparatus of the modern chemical battery industry. The lithium supply chain is a labyrinth of global extraction. It begins in the cobalt quarries of the Democratic Republic of Congo, bleeds into the lithium evaporation tracts of Chile, Argentina, and Australia, funnels through chemical refinement matrices, and terminates at an installation contractor who demands thousands of dollars to mount a degrading box to your drywall. Every sequential link requires aggressive financial extraction, and the engineered decay curve mandating replacement every decade ensures that corporate revenue stream is permanent. Domestic pneumatic storage requires a discarded steel propane cylinder, a fractional horsepower compressor, a rotary air motor, and $40 of standard brass fittings. The supply chain is a residential garage sale, a local hardware distributor, and a single afternoon of focused labor. No rare earth mining. No specialized technicians. No toxic end-of-life disposal protocols. But dealing with extreme atmospheric pressure demands absolute operational discipline. Converting a residual hydrocarbon tank carries severe lethal risk if poorly executed. This safety protocol is not optional. First, verify the steel collar bears a certification stamp for a minimum working pressure of 250 pounds per square inch. Second, open the primary valve in a heavily ventilated outdoor environment, completely devoid of ignition sources. Allow the volatile propane vapors to bleed out for 30 uninterrupted minutes. Third, completely flood the internal volume with liquid water to forcefully evict any remaining flammable gases, then drain it entirely. Repeat this aqueous flood cycle twice. Fourth, allow the open cylinder to stand vertically for 24 hours. Only then is the vessel neutralized. The architecture of the build is brutally simple. A 20-pound salvage cylinder forms the rigid heart. A direct current air compressor provides the pressure. A salvaged pneumatic motor translates that force back into rotational power. A 150-pound pressure safety relief valve is not a suggestion. It is a mandatory physical requirement to prevent catastrophic structural rupture. An analog gauge monitors the invisible tide. Total capital expenditure fluctuates between $100 and $170. It requires zero specialized tooling. Manage your operational expectations. This specific configuration is not engineered to sustain an entire residence. It is a tactical survival reserve. It illuminates the dark, fuels communication, and preserves critical perishables. These are the exact vulnerabilities that cripple households during grid failure. The ultimate triumph of this system is not raw capacity. It is aggressive permanence. The vessel capturing your compressed atmosphere tonight will harbor the exact same kinetic tension half a century from now. The chemical battery storing your energy today will store less tomorrow, on a predictable schedule concluding in a toxic landfill. You do not require rare earth metals violently ripped from 3 continents to capture the sun. You require a steel cavity, a mechanical pump, and an understanding of physical laws governing industrial engineering since 1870. Acquire a certified steel cylinder, purge the residual gases, seal the pressure of the atmosphere inside. We do not need to shatter the atomic structure of the Earth to capture its power. Sometimes, perfection is just empty space, waiting to be squeezed.